Today, we move into the really clever part of meshing. I want you to think about a complex model, like a fan we are going to work on soon. It has dozens of curved blades, tiny gaps, and complex shapes everywhere. If you had to select every single one of those features by hand to make a good mesh, you would be here all the week. It's an impossible job. So, how do we solve this? We don't do it ourselves. We turn on the Mesher's smart brain. Today, you will learn how to activate and control this automatic intelligence using two amazing tools, curvature and proximity. Let's start with the first tool, and it's all about getting the shape right. It's called Capture Curvature. Imagine one of the blades on our fans. It has a beautiful, smooth, curved edge. What happens if a mesh doesn't capture that curve? What if it looks like a set of jagged blockisters? Our airflow simulation will be completely wrong. The air will behave as if it's hitting a staircase or not a smooth blade. This is the problem that Capture Curvature solves. Its goal is to automatically find every single curve in a model. We are telling the software, I don't care what you do, but make sure that every curve looks perfectly smooth and realistic. It is the first step to creating a mesh that truly represents a real-world geometry. Okay, so our shape is now perfect, but what about the spaces between the shapes? This brings us to our second and even more critical smart tool, capture proximity. Think about our fan again. The most important physics happens in the tiny narrow gaps between the rotating blades. The air is squeezed and accelerated in these channels. If our mesh is too coarse in these gaps, if we only have one single straight cell, we completely miss this critical physics. Our simulation will fail to predict the fan's performance. Capture proximity is our hero here. Its goal is to hunt down every narrow gap in the model. We tell the software, find all the tidy spaces, and I want you to guarantee that we put a specific number of cell layers inside them. This ensures we have enough resolution right where the action is happening. This tool is the key to moving from a pretty mesh to a physically accurate one. Alright everyone, let's pause here and look at this slide. This right here is the whole story. This is the journey from a good mesh to a truly great mesh. We are going to use this simple U-shape to see exactly how these tools think. If we can understand this simple picture, then meshing our complex fan will be easy. Let's start on the far left. This is the basic mesh. The computer just follows one general size rule. Now, I want you to look closely. Is the U-bend really curved? No, it's a bit blocky, a bit jagged. And look at the narrow gap at the top. We only have one or two big straight cells in there. Is this going to give us accurate physics? Absolutely not. This mesh doesn't see the important parts. It's blind. Okay, so let's make it a little smarter. In the second picture, we turn on the curvature brain. And wow, look at the U-bend now. See how the cells are tiny and follow the curve perfectly? It's beautiful. We have captured the geometry, but I want you to look at the top again. What happened to the narrow gaps? Nothing. It's still blind to the gap. It was so focused on the curve, it completely missed the other important feature. This is only half the solution. So let's try something different. In the third picture, we have turned on the proximity brain. And look, the gap is now perfect. We have beautiful layers of cells right inside that channel. This is exactly what we need for good physics. But what happened to our beautiful curve? It's gone. The U-bend is blocky and jagged again. The measure was only looking for gaps and ignored the curves. Again, only half the story. So what is the secret? How do we get the perfect mesh? It's the final picture on the right. This is where we stop giving the measure half instructions. We turn on the full brain. We activate proximity and curvature at the same time. And now, just look, the curve is smooth and perfectly captured. The narrow gap is filled with high-quality cells. Every important feature is found and refined automatically. This is the intelligent, professional result we are looking for. This is the power we need for our fan. A fan has complex blade curves and it has narrow gaps between the blades. It needs the full brain. So now that you have seen the story on this simple shape, you're ready to unleash this power on our fan and see it work in practice. Let's do it. All right, so it's time to actually mesh our complex fan. And I guess this is a great example to show the application of advanced science functions. So, as you can see in here, we've got the whole actually rotor of the fan and also its blades all around a cylindrical part. And after adjusting that, establishing two separate zones, that is another concern in here, to just put it into a diffuser. This is the final geometry. So, as you know, for modeling a rotating part, we have different approaches. But when it comes to sliding mesh and also MRF or multi-reference frame, we need to have two separate zones. One is called the rotating one around the blades and also the rotating part. And the other one is the enclosure, or what we have in here is the diffuser. So let me just hide the diffuser. This is the blades and the rotor that is our main concern. So as you can see in here, the greatest and most difficult parts of this meshing is about these curves of the blades. If you can see it from upside, you can see that it is somehow stripped and this somehow exacerbate the meshing. So the other concern is the gaps between the rotating zone and the blades. As you can see, we need to fill this region with very tiny elements. And this is another challenge when it comes to this type of simulations. So it's not our concern to establish the model and how we actually did the steps to create these two regions. But now I just want to quit ANSYS space claim in order to open ANSYS meshing to proceed and look for a great approach to mesh this one using high quality grid. Very well. So let's start with this mesh grid. And what is important in here is that our mesh established from two distinct actually models. One is the enclosure, the diffuser, and the other one is the duct that is rotating. So I want to start with the initial defaults because I just want to see what is the results of the default values of the software, what we learned up to now, and is that actually sufficient to mesh this complex geometry or not. So let's just generate the mesh grid using the default values. Very well. So it successfully could establish the grid at least. And if we expand the sizing part, and if you remember, we called them the global sizing that we learned in session 3. It just applies the curvature mean size, the curvature normal angle, but no proximity to the whole parts, not just focusing on a local and a specific region. So we may be better to check the quality of that using, for example, the orthogonal quality. And as you can see, we have very poor grid, and most of them are around the blades and also the regions that we expected to have smaller elements. And it is pretty obvious because the default values could not capture the flow physics. So what is important in here, and I want to point out, is that this is the main reason that we cannot just rely on the global sizing. For example, for the curved surfaces of the diffuser, it was sufficient and it could create a high quality grid. But for the duct itself, it was not good. So from now on, I just want to suppress the enclosure and just focused on, I guess it was vice versa. I need to suppress the diffuser and unsuppress the dot. And from now on, I just want to focus on the rotating part where we know that we cannot create high quality grid with the basics and principles we learned up to now. So it could be an actually a great idea to create section plates to see what's going on inside and where are the poor elements. So This is the first section. You can see that around the blades, we could not actually track and capture the curves perfectly. This is called the jagged elements that we were talking in the slides. And maybe another section from this point of view could be perfect as well. So let's just have another section. And right now we can see what's going inside. So as you can see, the elements could not capture the curves of the blades, and it was pretty obvious because we didn't expect it to capture it with the default values. So from now on, it's our time to apply a local sizing. We learned some of the options from the previous session, and we already know that we need to apply it on the whole body, or we can also apply it just on the important surfaces. So let me just deselect these sections, and this time I want to apply it on the whole surfaces of the rotating parts, not the whole region. This is why I pick up the face selection tool, and instead of selecting all of them one by one, which is actually impossible, it's better to change a mode to body selection, starting from this point, drag and dropping to create a rectangle, and all the surfaces inside will be selected. So I want to apply a local sizing on all of these features, but also do not forget that we have some channels on this rotating part, and this is where the proximity comes in because it automatically can detect these regions, and also this space, the tiniest space between the blades and the rotating zone, and these are the areas that we expect proximity to capture. And for the curved surfaces, of course, the capture curvature is our best option. So I do not want to decrease the element size on the whole surfaces. Maybe, for example, we can come with 1 centimeter on the whole surfaces, but still we cannot do it less for all of the parts because it will dramatically increase the number of elements. Instead, we have another approach, which is the curvature and proximity. Curvature is on by default, so let's just turn on the capture curvature. And as you can see in here, we have distinct parameters that we need to learn. Very well, so let's start with curvature normal angle, the first parameter. This sounds technical, but let me give you a very simple picture. Imagine you have to draw a perfect circle using only short, straight lines. If I tell you to use a big angle between your lines, you will end up with something that looks like a hexagon or an octagon, blocky and blank. But if I tell you to use a very small angle, you will be forced to use many tiny lines, and your drawing will look like a perfect, smooth circle. This setting is exactly that. A smaller angle forces the measure to use more cells to capture the curve, making it smoother and more accurate. Then we have the min size, the second parameter ANSYS meshing wants. This is our safety rule. Sometimes a model has a tiny curve that is not important. We don't want the computer to go crazy and create a million cells there, so we simply tell it, hey, no matter what you find, do not create any cell smaller than this side I specify. It's a brake pedal to control the process. And then it comes the proximity parameters. Forget the text on the left for a second, just look at the 4 pictures on the right. These pictures show a simple channel or a gap. This could be the gap between the blades of our fan or the gaps and the channels on the rotating part. This is where all the important action happens. Now look at the first picture with the number 1. This is what happens if we let the measure put only one single cell across that gap. For CFD simulation, this is a disaster. A single cell can only ever calculate a single average velocity. It is completely blind to what's happening near the wall. This mesh will give you a wrong answer, guaranteed. But now look at this picture with the number 3. This is where the magic begins. This is our gold standard. By telling the software, I want 3 cells across the gap. We are giving the solver everything it needs. It can now see the bound layer near the top wall, the bound layer near the bottom wall, and the core flow in the middle. it can finally start to resolve the real physics. For a fan, getting at least 3 cells between the blades will be our primary mission. The picture with 6 and 9 cells show the level of control you have. For extremely high accuracy simulations, you might push this number ever higher. But for most industrial cases, 3 is the perfect starting point. So how do you give this command? We use the setting called num cells across gap. It is a direct instruction and it is the most critical parameter on this slide. Finally, just like before, like curvature, we have our safety rule. Proximity mean size. This is you, the engineer, telling this smart software, I need you to put 3 cells in the gap, but if you find a gap that is incredibly tiny, please don't make the cells smaller than this absolute minimum size. It's a brake pedal again to prevent the mesh from becoming impossibly large. Very well. Now you have the knowledge about these 4 parameters, and let's start by the default value for the curvature normal angle, which is 80 degrees. I guess this is enough for our curves. And also, I do not want to actually have a smaller cells with 1 millimeter in size. So both for the curvature capturing and also for all tiny channels. So our minimum size for elements would be 1 millimeter for all the parts. And then for capturing these gaps between the blades and the rotating part and also these micro channels on the rotating section, I do not want to fill with less than 3 elements. And after all, because we may not see every detail of our model, it would be best option to keep the faces and edges because we are now telling the measure to look for any tiny face and edge that needs proximity, gap factor, and min size to fill in with the high quality grid. So let's just have our next mesh because I just want to point out one more thing, which is very important. Of course, it is very important to create high quality grid, but there are some limitations. We cannot just go on and increase the total number of elements without any consideration. This is where the growth rate comes in. So let's just wait for the next grid. Alright, so it is gone and we can check the grid together. First of all, I want to get back to our mesh metrics using orthogonal quality to evaluate our final grid's quality. So as you can see, with simple proximity and curvature, mostly the default values could give us a very acceptable grid. As you remember, the minimum orthogonal quality was 0 in the previous one, the initial one. And now in our second try, we have 0.17, which is in acceptable range for orthogonal quality. So let's see what's going inside using these sections that we created. Of course, this is great, and this is why we were talking about proximity. First of all, this is the region that we know that the poor elements are generated in here, and the default values, I mean, the global sizings could capture the other surfaces somehow with good quality, but not this region. And right now, this is the power of proximity that could fill here with the best quality. And then it comes this actually channels on the rotating part. As you remember, we had them. And to capture the physics here, we needed the curvature tool. And let me just add the second section plane. And this is another great point of view. So this is our final one. We can export base grid and process the simulation into ANSYS Fluent because it doesn't need any other refinement. Uh, and if you just be more accurate on this, you can see in these areas that we have a dense grid, we have a smooth transition to the big elements on the left side. I mean, as far as we get from the blades and the surfaces, the curve forms, we having and watching bigger elements. But this can somehow fundamentally affect the number of elements. For now, the statistics shows that we have about 3 million cells. So there is another parameter that matters here because we specified a local sizing on all of the curved plates, but we need to set that how we wanna have transition and manage it through the bigger ones. And by default, you can see 1.2 is the choice of ANSYS font, or let's say ANSYS meshing. So let's see what is this parameter with a better example. Okay, this is our final and most important parameter. It is called growth rate. So think about it. We have used our small tools to create beautiful tiny cells right on our fan. And far away from the fan, we want big, simple cells to save computer power. The question is, how do we connect the small cells to the big cells? We can have a sudden jump. A sudden change in cell size is like a giant butthole for the CFD solver. It creates errors and can make our simulation unstable. The growth rate is the answer. It controls how fast the cells are allowed to grow. It builds a smooth bridge between the small and large parts of the mesh. Now, let's look at the proof right here on our fan. This is not a theory, this is a real example that we had. On the left is the default setting of 1.2. This means each new layer of cells can grow by 20%. Look closely at the transition. It's a bit fast and a bit aggressive. It's okay, but it's not perfect. Now look at the right. Here we made one tiny change. We made the growth rate smaller, just to 1.15. And look at the incredible difference. The change from small cells to big cells is so much more gradual, so much smoother. This is the high quality result we were looking for. And yes, look at the numbers. This one small change added over 500,000 cells. But these are good cells. These are quality cells that create a stable, reliable mesh. This is the difference that will give us a better, more accurate simulation results. And with that, you now understand all the secrets to create an amazing automated mesh.